time t, and choose action A sub t at time t, this is the probability that we end up in some state S prime. So once the action is taken, there's some distribution, and we're assuming that that's fixed over time. But possibly unknown to the learner, right? So what makes the reinforcement learning problem different from, say, solving a Markov decision process given a specification is it's not given a specification. There's the rewards and transitions are unknown. You have to do some amount of experimentation to find out how they work. It turns out if you do know R and T, though, there's wonderful algorithms for deriving optimal behavior, maximizing expected discounted reward. And this equation kind of summarizes almost all of those approaches. This is known as the Bellman equation, and it goes like this. We want to estimate the long-term reward that I get, or that the agent gets, starting off in some state S, if it takes action A first, and from then on behaves optimally. So it's sort of one free action, and then after that, it's somehow magically knowing what to do and behaves optimally. How much reward does such an agent get? Well, it gets whatever the immediate reward is for taking that action from that state, and then it makes the transition. Where does it end up? Well, it ends up in state S prime with probability T, SA S prime. So we're going to sum over all possible next states, weighted by their probability. We're going to discount it one step, geometrically, because it's one step in the future. And what does the agent do when it gets to that state S prime? Well, we're going to assume that it already knows this magical Q function, which says for the state that it's in, S prime, how good would it be to take each possible action as its first action, whichever one gives the highest expected reward, that's the one to take. So we're going to max over all possible next actions the Q value of those next actions. This Q is the same as this Q, so we have a system of equations. It's not immediately obvious how to solve this, but there are methods. For example, mapping it to linear programming and then solving it using the linear programming algorithm is an effective way of actually solving this planning problem, deriving the Q function, and then once you have this Q function, the optimal action to take at time step t is just maximize over all actions the Q values in the state that you're in. Okay? So if we knew the model, we've got algorithms that can handle that, that can generate optimal performance, and it'll go and act in the world. But that doesn't tell us how to learn, right? It doesn't tell us what if you don't know the transitions and rewards. If you don't, well, now you can't do this, and even if you could, you wouldn't necessarily want to because you have to experience more of the environment as you go. So in case this wasn't clear so far, we can map that dog finding the ball problem to a Markov decision process. In fact, that's more or less what we did. We can think of all the orientations of the dog in space as corresponding to different states, and the actions that it can take left and right correspond to transitions as it sort of moves around this circle of which way it's facing, and there's one, in this case, distinguished state that has positive reward, and all the other ones have either a small cost for moving or just nothing. Okay? So we can frame questions about behaving in the environment as Markov decision processes, and then think about what it means to derive optimal behavior in them. Given that we don't know the transitions and rewards, it turns out the field is focused on two main classes of algorithms for doing the learning part, deciding what to actually do when you don't know T and R at first. And I'm going to describe both of them because we have efficient algorithms in both classes. The model-free case says, well, there's this magic function Q that tells us that is all we really need to know to decide how to behave. In model-free learning, we use our experience directly to estimate this Q function. So it's a cartoon version of Q. It's not the real Q, it's an approximation. It's a caricature. And so there's algorithms like Q-learning and SARSA that are very well studied for doing this. Most of our work in our lab has been on model-based learning, and what that does is it uses its experience to actually estimate the transitions and rewards, and from that, it computes an estimate of the Q function. Okay? And there's a class of algorithms that have been shown to be effective in that setting. So just pictorially, if you want to get a sense of this, in the model-free case, we're saying we go from experience, which are just lists of the agent was in some state, it took some action, it got some reward, it ended up in some next state, it gets a whole series of this as its experience. From that, it estimates the Q function, and from the Q function, it takes actions. The model-based approach goes a different path. It estimates the transitions and rewards to get the Q function, and it uses that to act. So those are pretty much the two main classes that you could approach. Here's how Q-learning looks. If you are interested to know that, on each time, it's trying to keep an estimate of the Q function. Each time it gets an experience tuple, right? It went from some state to some next state, given an action and reward. This is what it does. This is like the whole algorithm right here. It's very nice. All you have to do is update the Q value for the state action pair that you just left to make it what it was, plus a little bit in the direction of whatever the immediate reward was, plus the discounted max value of the state that it ended up in. So it just takes whatever its old estimate was and it bumps it a little bit towards the reward plus the discounted value of the next state. And what's cute about this is, well, first of all, you can code it with more or less one line. Almost the whole program, if you do this, is all about connecting that algorithm to the actual environment. But the learning algorithm and the behavior stuff in and of itself, it's just this. And as a result, there's been way too much research on it. Because it's not a great algorithm, but it's elegant that it's so short. I mean, I guess another powerful algorithm would be, behave randomly, and if that gives you optimal rewards, stop. Just take that as your final behavior. That would be another very slow algorithm. This one I think is a bit better, but only a bit. So what we know, though, is if all state action pairs are visited infinitely often, so if you actually explore enough of the environment, and the learning rate here decays at the appropriate rate, then the estimate of the Q value converges to the true Q values in the limit. Okay, so that gives you some warm and fuzzy feeling. A model-based learner is similar. It's just doing its updates on the rewards and transitions, and then it computes the Q values by solving the Bellman equation. So these steps are really simple. This step is very heavyweight. This is a big computational optimization that it has to do to derive the Q values and use that to act in the world. But you can show that the Q values will go to the true values. It's sort of obvious, but I wrote it in my thesis, so I cited myself. I don't want to claim any big results there. It's actually pretty straightforward. But the problem with these results are that they're just saying, in the limit, it will be optimal. So your learning algorithm, your robot, will eventually be optimal if you wait till the end of time. And at some point, you're like, I'm tired of waiting till the end of time. So you really want to have something better than that. Being truly optimal in a finite amount of time is actually not entirely possible. It's like estimating the probability that a coin will come up heads with perfect precision. Which, you can keep doing it and improving your estimate, but you never really get the exact number, unless, except in the limit. So we don't expect that. We want near optimality, something that will behave close to what an optimal policy would do, but it's okay, we can tolerate a little bit of error. In fact, if we're really unlucky, we might not even be able to do that. So we really want something that's approximately correct, probably. So that's what PAC is about. And this is due to Valiant back in the 80s, this sort of notion that we're going to have learning algorithms that, well, we need to kind of loosen up on what true optimality is, but it's still hard to hit this, and it's maybe good enough to hit this. So this was first in supervised machine learning. It was extended to reinforcement learning in a series of papers. And the gist of it is this. I can tell you the gist of it, which is somebody tells our learning algorithm in advance some number epsilon, which is how close to optimal it should be, and some number delta, which tells you how far from certain you should be that this is correct. So they both need to be away from 0. It knows how many actions and states there are and the discount factor, but it doesn't know anything about the transition diagram other than that. It has to start experiencing it. And we're going to say that as it's experiencing in the world, as it's choosing actions, every time it chooses an action at time t that is more than epsilon worse than what the value of the true action, the best action in that state, we'll call that a mistake. So every time it takes a step in the world that isn't among the top choices, the most reward-evoking choices, it's going to get a tick. And it's going to now try it. Now m is going to be bound on the total number that it's going to get, and that bound has to hold with high probability, and we want this bound to be polynomial in, say, actions, rewards, how close to optimal, how sure, and something about the discount factor. So that's the task. This isn't telling you how to do it. It's just telling, setting a goal up. But what's good about this goal is the only way to achieve it, you really do have to balance exploration and exploitation. You need to be exploiting by taking near optimal actions almost all the time, but there's no way you can do that, given that you start out in a world that you don't know, without some amount of exploration. So these things have to be balanced against each other. There's other, yeah, go ahead.
How do you know whether your step was max A?
The agent doesn't actually. The agent has to behave in a way such that this is true, though it itself doesn't actually know what Q is. But it turns out that
the wise researcher did.
Yeah, with the algorithm designer, it can prove that at least if you set the parameters wide enough, this will hold. Just like if you flip a coin a bunch of times, you might not know what the real probability of heads is, but by things like the Hufting bounds and the turnoff bounds, you can know that after you've estimated it based on a big enough sample, you're within epsilon. It turns out to be very close to that kind of result.